Hello, my name is David May and I was brought into the IOF Photo Commission some time ago to help set up the World Ranking System from scratch. This is the second of 3 short videos which explain how the system was developed and how it works. It focuses on explaining the principles which govern the algorithm which calculates ranking points at each event without going into the details of the formula used. Part 1 of this series of videos examined the weaknesses of alternative scoring systems. It used these to develop the criteria needed for a ranking system to be fair and showed the need to devise something which meets these criteria. Firstly, we've already shown that the scheme must be based on each runner's time and not on their position. And to be fair to the whole field, we should have each minute in the race worth the same number of points as well. Then we must take into account the strength of the field. Are the top runners there or not? And is there a big spread of ability or a small one? As we have seen in part 1, the spread of times in a race varies with the nature of the terrain, so this spread must be taken into account too. And the good news is that the system we've had in place for over 20 years now meets all these criteria. What next? We know how to measure time for criterion 1, but we need also to understand how we judge criteria 2 and 3 above, the strength of field and the spread of times. Part 1 also showed that the strength of the field depends on who turns up. Again, are the top runners there? Is there a big spread of ability? The best way to judge this is by seeing how the runners performed in the past. This is easily shown by the average of their previous points. In practice, the points gained in the previous 24 months. As an example, suppose we have a race with just 5 runners, A to E, whose average previous points are as shown. Assuming that 1000 represents the average of all runners, then it is clear that all these runners are well above average, and that there is a small range of only 100 points between them. A different 5 runners, F to J, compete in a different event, with points as shown. Now it's clear that, although there are some good runners, there are also 1 or 2 not far above or below the average as well. There is a large spread of ability. We conclude that the strength of the field can be determined from the spread of their previous points as well as their average value. Criterion 3 was about the effect of different terrains on runners' times, so it would help to look at a further example to illustrate this. The results list shows 2 completely different events, 1 and 2, with 5 runners, K to O, competing in event 1. A different 5, P to T, take part in event 2. Their race times are shown and both winners take the same time of 40 minutes. Times are less spread out in event 2, so it looks as if it was held on less challenging terrain than event 1. But can we be sure of this? So, is event 1 more physical and or difficult than event 2? Or did event 1 have runners who are more spread in ability? Or is it a combination of the two? The answer is that we cannot tell just by looking at the results. We need to look at the spread of runners' previous points to see what's really happening. Before going any further, it helps to look at previous points obtained by the whole cohort of runners, men in this case. The column chart looks at the average points gained by the 3,000 plus men in the IOF database in the period 2018 to 2019 and bands them into groups of 50 points. The chart plots the number of runners in each band, the height of each column being this number. For example, the column outlined in yellow shows runners with previous average points between 1200 and 1250. Its height shows there were 170 runners with these scores, and the rest of the columns are plotted in the same way. The average of all these values is 1000 points. We now overlay the column chart with the well-known bell curve, with its peak at 1000, the average value of all the runner scores. Yes, there are departures in reality from the smooth bell curve, but overall there's a pretty good match between the points distribution and the bell curve. This means that we can, with a good degree of validity, apply the statistics of the bell curve to our ranking system. But first, we need to look at bell curves a little more. The two we can see here both have a mean or average value of 1000, which corresponds to the peak of the bell. However, the values on the left are more spread out than those on the right, which has a taller peak as a result. The task we have is how to measure the two spreads. The beginnings and ends of each curve are hard to define. In theory, they keep on going, getting closer and closer to zero, but never quite reaching it. So statisticians have devised a measure called the standard deviation, or SD, where it turns out that a fixed proportion of all values lie within one standard deviation from the mean. This proportion is always 68%. The left-hand graph shows an example where the standard deviation is 200. One standard deviation above and below the mean is thus 200 above and 200 below 1000. The range of values in this range is from 800 to 1200. The yellow area represents the 68% of values mentioned before. The right-hand graph shows the result of having the same mean of 1000, but halving the standard deviation to 100. Finally, the left-hand chart shows how many values there are if you go two standard deviations from the mean, from 600 to 1400. It turns out that 95% of all values are in this range, or 2.5% would be above 1400 and 2.5% below 600. From an orienteering point of view, scores of over 1400 and below 600 would be rare. Distributions in practice are never as perfect, however, as shown by the chart we looked at earlier, of previous points of all runners in the IOF database. This time the standard deviation of 200 is marked on. The other spread we've been considering is that of race times. Can we treat these using the statistics of bell curves too? The chart shows times taken in 5-minute bands for all runners in the 2019 men's JWOC results. They are clustered in the middle and spread out at either end, so roughly follow a bell curve as shown by the overlay here. The mean is just over 80 minutes and the standard deviation is 12 minutes. It's clear that the standard deviation forms an effective measure for the spread of times, and we can describe the results of this race in terms of the mean time and the standard deviation in time, each of which can be calculated readily from the results. We spent some time in exploring the concepts which the rankings system employs, so now is the time to see how they are used. In order for the rankings calculation to be valid, we need to make some assumptions. Firstly, that runners' time in a race are distributed in bell curve fashion as those for JWOC 2019 roughly were. Secondly, that overall, runners' points stay the same after the race as before. This doesn't, of course, mean that nothing changes. What it means is that some runners do better than expected and their points go up, and that this is balanced by those who do worse, whose points go down. So whilst individuals' points will change, the average for all the runners is unchanged. Their mean points stay the same. So a race with good runners will find that the runners get good points, whilst the less good field will earn less good points. The other feature of points after being overall the same as points before is that the spread of points must stay the same. A wide spread of ability will generate a wide spread of points, for example. Both of these factors, mean and spread, define the quality of the field. Let's now look at an example of how these principles drive the ranking scheme. Suppose there are 10 runners, A to J, entered for a particular race, and their previous points are as shown. Separate calculations give the average or mean of their points as 946, and their standard deviation is 100. A different way of looking at this is to plot the previous points on a vertical scale, where their distribution is more clearly shown. Runner A has the best previous points and J has the worst. The mean points of 946 are now shown by the blue arrow, and the spread of points being measured by the standard deviation are now related to the distribution more visually. Note that in this example, all but runners A and J have previous points within 1 standard deviation of the mean. As we know, these two values measure the quality of the field. In this case, the runners are a bit below average in ability, as their mean is less than 1,000, but there's not a particularly big spread in their ability, as the standard deviation is at the lower end of the values we observe in practice. The race has been completed, and each runner's race time in minutes is now shown. As is highly likely, they don't finish in the order of their previous points, as some, for example runner C, do better than predicted and some do worse. Field quality has already been determined by the mean of 946 and the standard deviation of 100 points. So next, we need to know the mean and standard deviation of race times. Calculations show these to be 54 minutes and 10 minutes respectively. If we plot these race times on a vertical axis, we get a better visual interpretation of how they are spread out. The mean time of 54 minutes is now shown by the blue arrow. 1 standard deviation better is 54 minus 10 or 44 minutes, and 1 standard deviation worse is 54 or plus 10 or 64 minutes. We now show distributions of the previous points and for race times side by side. The two blue arrows remind us that the average previous score for the runners was 946 points and that the average race time is 54 minutes. Because of the principle that the mean and spread of the points stay the same, the average time must correspond to the previous mean score for the group when we allocate points to each runner. In this case, a time of 54 minutes must correspond to a score of 946. The example has been chosen so that there happens to be one runner, F, whose time of 54 minutes is actually the same as the average time for the race. So runner F, who has the average time for the race, gets the average points, which are 946. Next, the race time, which is 1 standard deviation better than the mean time of 44 minutes, must correspond to the points which are also 1 standard deviation better than the mean points, or 1046 points. By chance, runner A took 44 minutes, so he is awarded a score of 1046. Finally, the time which is 1 standard deviation below the average time, that's 54 plus 10 equals 64 minutes, is matched to the score which is 1 standard deviation below 946, i.e. 846. The chart summarizes what we have all in one place. Using the fact that 100 points corresponds to a time of 10 minutes, it's clear that each minute is worth 10 points. And this allows us to fill in all the remaining points as shown by the red column. An up-down column has been added to show how each runner's points compare with their previous average, and it's clear that they're not all the same. Runner I has had an excellent run by previous standards and is 127 points up on their average. Runner A won't be so pleased, however. Finally, we need to check that the mean and standard deviation of the new points are exactly the same as before, as indeed they must be and are. This video has explored how ranking points depend not just on race times, but also on the quality of the runners in the race. We show how the pool of previous points is used to determine what points are allocated after a race. This is done by mapping their mean and spread to the corresponding mean and spread in race times. We also note that the spread is defined as being the standard deviation. The basic algorithm is still at the core of the current ranking system, but various modifications have been introduced over the years. Part 3 deals with these and also explains how the Athletes World Ranking List is generated.